So in previous class, in previous session we discussed about, that is, components of module. We also call as components of module, or we mentioned a block diagram of a module. So in previous class we discussed a components of module as well as we take one example, that is SR latch. So it belongs to what? A sequential circuits. So in SR latch what? We are not applying any clock. Let us take one more example, that is continuation with respect to a previous class. So that is D flip-flop. So here we know that D means data in, or simply we called as a data flip-flop. So before going to what? Any programming, okay, before going to a components of module, first we have to write the what? A block diagram and as well as a truth table. Then based on the truth table we have to write the what? A code here. So in previous program, in previous SR latch, we have to use a gate level description, because in that logic diagram we are using NAND gates. Okay, that's why we have to use a gate level description. Latch is what? We are not applying any clock for the latch. We simply apply the reset and input and outputs. So here the flip-flop is what? It's sequential circuit. Output depends on the present as well as past, and also it depends on the variation of clock. So that's why the flip-flop is always right in terms of a behavioral description. Means the based on the truth table we have to write the a code. So before going to write the code, the first we have to what? Write the block diagram of D flip-flop. So this is the name it as D underscore flip-flop. So we know that inputs. So D is the input, then so one more, the clock is the another input. Then for sequential circuit we always choose reset input, because when you apply the reset then everything is what? Reset means everything is 0. So that's why we consider a reset here. Then after this we have to mention the output. So output is Q. If you want Q bar, then you can write the what? Q bar 1. So after this, so we have to write the what? A truth table. So what are the inputs here? D is the one input. So what are the inputs? Then D is the one input, then clock, then reset, then finally Q is the another one. So initially we have to consider then D is equal to 0. On that time we have to write clock edge triggering. Okay, so you can write edge triggering, or you can write simply this one. Okay, it indicates it's an edge triggering one. So but we always write a standard format. So that's why here clock is, it indicates it's a positive edge triggering. Suppose it's like this, then it becomes a negative edge triggering. So we always choose a positive edge triggering. Then reset, it may be a 0 or 1. So initially we consider reset is equal to 1, and that time it D is equal to 0, positive edge clock triggering, then reset is equal to 1, then obviously Q is equal to 0. So next we have to consider D is equal to 1. Again we have to consider a positive edge triggering, and that time again reset is equal to 1. Then here reset is equal to 1 when D is equal to 1. So here Q is not directly proportional to D because of reset is equal to 1. Though obviously then Q is equal to 0. Then next we have to consider 1 again, then positive edge triggering, then reset is equal to 0. Then reset is equal to 0, then whatever input you applied, that is directly proportional to output, that is Q is equal to 1. Okay, next take one more one, then D is equal to 0. On that time here we have to suppose it's negative edge triggering. So on that time there is no change here. Whatever input output previous state, that should be what? Continue here. Okay, that is the what? A truth table for D flip-flop. So based on this truth table we have to write the what? A module components of module. So first the always start with module, right? So module, it's predefined word, so name it as D flip-flop, that is the name of the module. So after the name of the module, here you have to write the module terminals. So what are the terminals here? D, clock, reset and Q. So we have to write the what? Terminals only. Then D, then clock, reset, then finally Q. So these are all the terminals with respect to D flip-flop. So once you write the terminals, so next step is what? We have to mention inputs and outputs. So what are the inputs and outputs are available with respect to D flip-flop? So what are the inputs here? The input, then input is what? A D is the one input, then clock, then reset. So and with semicolon. Then after this you have to mention the output. Output, then Q. So here one difference compared to previous one, in gate level description we are not using what? Any storage element, but here this is sequential circuit, this is the flip-flop one. So we have to write the with respect to behavioral description. So in behavioral description, output is always acts as a register, that is the keyword is REG Q. So this is the what? A declarations of ports, that is input and output ports. So once it is done, next move on to very important one, always. Okay, always is predefined word with respect to behavioral description. Always at, we have to consider positive edge here, there is no bubble. So pos edge clock, always at pos edge clock, then once always at pos edge clock, then if reset, you can write if reset or if reset 1, both are same. If reset means reset is equal to 1, or you can write reset is equal to 1, same meaning. So if reset, then on that time you have to observe the truth table. If reset, what happens here? If reset, then Q is equal to 0. If reset, Q is equal to 0. Else, other than reset. So other than reset, so output depends on what? This one, D. Okay, when it is positive edge triggering. Okay, when it is positive edge triggering, then output depends on whatever input you applied, that is Q is equal to else, Q is equal to D. Then end module. So this is the what? A design block we have to discuss. So again I repeat this. Module, name of the module is D flip-flop. So inside the module you have to mention the different ports. So what are the terminals are available, that is D, clock, reset and Q. Then after this you have to mention the what? List the ports. So here two types of the ports, one is input, another one is output. Input is D, clock and reset. The output is Q. So output is Q. In behavioral description or sequential circuit, you have to store the data because the output depends on the present as well as past. So that's why we have to write in terms of register, that is keyword is REG Q. Then one up to this one you have to indicate what? List the inputs and outputs. So after this you have to write the module internals. So what are the module internals available here? Always is predefined word, is always, start with what? A behavioral description, always at pos edge of the clock. It indicates when it is pos edge of the clock, then this operation. So first condition, if reset. So if reset is equal to 1, then Q is equal to 0. Else, okay, other than reset condition. So if here, then it should be what? Else. So there are two conditions here. Okay, reset is equal to 0, then reset is equal to 1. Initially you have to apply reset is equal to 1, then after else means reset is equal to 0. Then reset is equal to 0 here, then Q is equal to D. So whatever input you applied, that is directly proportional to Q, then end module. So this is the what? A design block. Next we have to write a stimulus block. Once the design block is completed, so we have to test the what? Code. So that can be done by a stimulus block. So the stimulus block is always start with a module. So name of the stimulus, you can write any name. That is, you simply write as stimulus here. Stimulus is the what? A name of the a module with respect to a test bench or stimulus block. Then after this, here wire acts as a output here. Okay, so in stimulus we have to write the wire acts as a output. You simply write wire Q. Here the output here in design block here you have to use keyword output, but in stimulus block you have to write wire. Then after this, resistor, that is what are the input terminals you have to mention, that is resistor D, then clock, then reset. Wire acts as output, resistor acts as a input. So once that is stimulus declaration is, that is ports is done, next we have to what? Instantiate a design block with respect to stimulus block. It's very important one. So instantiate design block and stimulus block here. So what is the name of a design block? So we have to write here DFF. You name of the what? A stimulus block. Okay, you have to name it as, that is instantiation. The name of the instantiation I can assume here R1. So inside the here you have to write the what? Inputs and outputs. So obviously here same name you have to assume. So you can easily write D, then clock, then reset, then Q. Okay. So one more way to what? Instantiation, that is we will discuss in laboratory. Okay. For theory part we can write a instantiation, the name what here, first you have to write the design block name, that is DFF. Then R1 is the name of the instantiation. Then after this you have to mention the inputs and outputs, D, clock, reset and Q. So up to this one, this is an instantiation. Next we move on to what? A important one. We have to apply the inputs and input data here. Okay. So first you are using keyword initial. So initial, then after initial. So first you have to initialize the clock because the output changes with respect of the clock. So that's why we have to initialize the clock, that is clock is equal to 1 binary 0, or we simply write 0, it's not a problem. Okay, 1 binary 0, that is if 1 indicates it's in 1 bit, a binary 0. So clock is what? It should be changes continuously. Why? Because it works only a negative edge of the clock. So that's why here we are using keyword always #5, then clock is equal to not of the clock. So it means clock is toggle every 5 nanoseconds. Okay, every 5 nanoseconds clock is continuously toggles. So clock is toggles every 5 nanoseconds. So after this I have to mention the what? Again reset operation. Again we are using initial. So we should use a begin. Why should we use begin? Because here initially we have to apply the one data here, that is clock is equal to 0 only. We have to apply one or more data and two or more data, and that time we should use begin. Initial begin. Then after this reset. Okay, reset initially is always 1, and after this some 10 nanoseconds reset, it becomes an 1 bit 0. After some 10 nanoseconds, then reset become a 0, and that time only the flip flop is working. Then after this we are using, there is a what? A begin is predefined word, that should be end. Up to this one we have to what? Apply the data. Next we go to what? Monitoring the data, as well as we have to display the data. Okay, that is we already discussed in previous classes, that is monitoring operation and displaying operation. So here we concentrate on monitoring operation, that is always start with $monitor. Inside the monitor you have to mention time, so that indicates $time, we already discussed, that indicates a current simulation time. Then after this, important thing is you have to apply the what? Some data here. So what are the data here? The clock and reset. That is, it should be what? In terms of a binary data. So that's why clock is equal to percentage B, then comma reset is equal to percentage B, then after this Q is equal to percentage Bn. So it indicates a new line, then comma, then clock and reset. So one more is there, that is D is equal to percentage binary. Okay, that is end module. So of monitor we are using because it monitors the current simulation time. When the simulation time is changes, on that time you have to what, monitoring the current simulation time, as well as it display the what, a results. So that's why instead of display we always choosing monitor. So $monitor, it indicates a calculation the current timing time. Next we have to what, declare the a data here. So we always choose a binary data. That's why clock is equal to percentage B. We already discussed, it indicates a binary data. Then D is equal to percentage B, it indicates a binary data, again D, reset, again it's binary data. Then its output also it displays in terms of binary, that is percentage by slash n, it indicates a new line. That is next line, you have to display the D, clock, reset and Q. Okay, then end module. This is the what, a stimulus block with respect to a D flip-flop. So let us take up to this one. The first one, SR latch, we have to write gate level description. Okay, then next one, this one, that is a D flip-flop, we have to write in terms of behavioral description. So next one more is there, that is data flow description. We have to consider data flow description. So example here we have to take, that is off adder. That is very simple example with respect to combinational circuit. We have to consider one more example, that is off adder. It belongs to a data flow programming. So we have to write the data flow programming here. So before going to what, a programming, first we have to write the what, a truth table, then logic diagram, that is logic circuit. It's very important with respect to what, off adder. Why logic circuit and equations is important? Because here we have to write the what, code with respect to data flow programming. First we have to write the simple block diagram for off adder. So that is name it as HA. Then we know that inputs, that is A and B is the input. Then what is the outputs? Then sum and carry. Sum and carry is the outputs. Next we have to write the a truth table for this one. So based on truth table we have to write the equation. Based on equation we have to write the logic circuit. Truth table, then A, then B is the inputs, then sum and carry is the outputs. So here there are two inputs, there are four combinations. If it is 0 0, then obviously sum is equal to 0, carry is equal to 0. Then if it is 0 1, on that time sum is equal to 1, then carry is equal to 0. Then it is 1 0, then sum is equal to 1, carry is equal to 0. If it is 1 1, on that time sum is equal to 0, then carry is equal to 1. So here I directly write the what, equations of off adder based on this truth table. Then first we have to write the sum equation. So sum equation, where it is 1 here, logic 1 here. Okay, in logic 1 A is equal to 0, then B is equal to 1. So A is equal to 0, it means A bar, then B, right, B is equal to 1. So here next one, when sum is equal to 1, and that time A is equal to 1, B is equal to 0, that is A, B. So instead of this one we have to write the what, a simple equation, because suppose you use this equation, and that time it requires two NOT gates, that is A bar and B bar, then two AND gates, that is A bar B, then A B bar, then one more OR gates. So that's why we simplified this equation. So this can be replaced by XOR gate. We simply write A is XOR B. So after this, once the sum equation is completed, we have to write the carry equation. So in carry equation, so when it is 1, and that time AB, so you simply write AB. So it indicates A and B. So after this here you write A, and B. Okay, this is the symbol of AND gate. So once the equation is completed, so based on this equation we have to write the code, and before writing the code we have to write the logic circuit. So logic circuit, one XOR gate, one AND gate is required. So here write XOR gate. So A is the input, then B is the another input, then it produces sum. Then for carry, again A is the one input, then B is the another one, then it produces AND gate. Then that is carry. So this is the what? A simple logic circuit with respect to half adder. So based on this equation, that is sum is equal to A XOR B, then carry is equal to A and B, we have to write the A code, that is design block as well as a stimulus block. So based on this equation we have to write this code. Then code is always start with module. So name of the module, simply write HA, it indicates name of the module. So inside the module you have to mention the terminals. So what are the terminals here? That is A and B is the input, then sum and carry is the output. So here I will assume A, B, then sum, yes, you have to assume, then carry. You have to mention the input and output ports, that is input A and B, then output S comma C. So this is the what input and output you have to mention. Then after this is data flow programming we have to use here. Okay, data flow means we have to consider these equations. So first equation, sum is equal to A XOR B. So here the XOR symbol is in Verilog is this one. Then this is what AND symbol with respect to a Verilog HDL. So next we have to write the equations. In data flow is always start with assign keyword. Okay, we discuss later again. Okay, in next classes. So next it's always start with what? Assign. Assign is the predefined word. Assign, that is A, S, you have to assume here sum. Assign S is equal to A XOR B. Okay, next again we are using assign. Next carry one, that is C is equal to A and B, that is A and B. Then AND module. So up to this one it's a design block. Next move on to a stimulus block. So in stimulus block it's always start with a module. So that is name of the module, you can write any name. That is here we have to assume a stimulus, that is name of the module. Stimulus is not a predefined word. Then after this register acts as a what? Register acts as a input. We already discussed register acts as input. What are the inputs here? Reg A and B. So it belongs to only what? A stimulus block. So here register A and B, because why we consider A and B, A comma B register here? Because we have to store the data here. Then wire, so outputs, that is S comma C. Then after this instantiation, it's very important one. So instantiation, first we should write the what? We should retain the a design name, that is design block name, that is HA. That is next we have to write the name of the instantiation. We can simply write H1, R1, you can write any name. Then after this inside the what? Instantiation you have to mention the inputs and outputs, A comma B comma S comma C. Then after this we have to apply the data for inputs and outputs. So here there are 4 combinations here, right? So there are 4 combinations. Initial, so begin, initial begin, then it's very important one. So initially A is equal to 0, B is equal to 0. That is a first initialization, A is equal to 0. Then after 5 nanoseconds, so A is equal to, based on truth table, A is equal to 0, then B is equal to 1. Okay, next after 5 nanoseconds, then A is equal to after 0 0 0 1, then 1, then B is equal to 0. Then after 5 nanoseconds, then last combination A is equal to 1, then B is equal to 1. So this is the 4 combination you have to apply. After this 4 combination, we have to write the what? It's a begin. So it's always end. Okay. Then after this, then after end you have to write the what? A monitoring the information. So that is always start with $monitor. So in $monitor we have to calculate the current simulation time, that is time. So after this you have to mention the what? A inputs here. So what are the inputs here? You have to write double quoted, that is A is equal to a percentage, B it indicates it's an binary one, then after this B is equal to percentage B, it indicates again it's binary, then after this we have to what? Display the outputs here. So what are the outputs here? That is a S is equal to B, that is should be what? A new line, then comma, then carry C is equal to percentage B, that should be what? A new line. So after this it's quoted is closed, then after this you have to what? Display the information, that is what are the displaying here? That is A, comma B, comma S, comma C, that is ended with semicolon, then after this finally end the module. Okay, this is the what? A stimulus block with respect to a off adder circuit. Again I repeat this, here register acts as inputs A comma B, wire acts as a S and C, why register acts as A and B? Because we have to store the information here. Then instantiation, HA is the name of the design block, then H1 is the name of the instantiation. So what are the instantiation parameters here? A, B, S and C, that is A, B, S and C. Then after this we have to initialize the data, initial, begin. Why we are using begin? Because there are 4 data we have to apply it, that is 4 combinations. So if it is one combination, begin is not required. Okay, there are 4 combinations here, begin should be required. A is equal to B is 0, B is equal to 0, that is initialize the data, then after 5 nanoseconds 0 1, then again after 5 nanoseconds 1 0, after 5 nanoseconds it's an 1 1. There are 4 combinations. So once it is done, there is a begin, is always end, that is keyword. Then next we have to monitor the current information, because so here the current information simulation time, it's very important one. Okay, we have to monitor the what? Current operation. So that's why we directly go to monitor one. So if you don't want the what? A current simulation time, on that time instead of $monitor we write a $display. Okay, so $monitor time, it indicates current simulation time. So A, B, C, A, B, S, C, so all are binary one. Okay, it should be binary, then /n indicates its new line, then display the what? A, B, S, C, then end module. This is the what? A stimulus block, a stimulus program with respect to off adder example.